So we have just summarized about the scanning electron microscope. Next is the transmission electron microscope. Also, I'm just going to refer it as the TEM. So the term transmission, as we have mentioned, is literally electrons that comes out from the other side of your sample. And these two are a very common or old school type of TEMs that are present. You can see there are very big straight columns going straight down. And in this session, what we're going to do is to focus on what is going on inside any of these TEMs. Of course, your TEM might not be the same as the TEM that we have here, but the concept is similar, and there are going to be probably much more advances depending on what brand, how much you paid for it. But again, as I said, the principle still applies. So let's start with what information we can obtain from TEM. Okay. So we're looking at the bottom part, so the transmission things. We can get the inelastic scattering information, which is the EELS, the electron energy loss spectrum. We can get the coherent elastic scattering information, known as SAD or CBD. And of course, sometimes it's just not diffracted at all and it goes straight out. Okay. Now, from this slide, I want you to remember is that for transmission, the specimen needs to be very thin. Okay? Otherwise, the electrons will be accumulated inside your specimen, and then it will probably absorbed and be termed as heat, and then it will cause damage to your specimen. So please be thin in relative terms, thin enough for the electrons to see as transparent, to be thin enough that the electrons not only be able to transmit sufficiently through your specimen, but also have enough intensity to force onto the screen or the CCD to allow interpretation in a reasonable time. Right, so let's talk about what things we can play with in TEM. Now, in TEMs, instead of just static informations, nowadays we're really popular in, we call it in situ holders. The term in situ holders means we can now apply different conditions and see how your specimen or how your sample reacts to that particular environment. So from the first one is we can add heat. So remember what I said, heat is bad unless it is intended to be there. Well, this one is we intended it to be there. For materials engineers, needless to say, the importance of heat to materials characteristics. So it tends to change forms, crystal structures, and things like that. And of course, materials behaviors changes under heat is in microscopic scale. So that's why we use TEM to study such things. For these sort of TEM probes, it can go up to 1,000 degrees Celsius. But please remember when you're using this heating probe is that what is your material? Can your material go up to this temperature? For example, this is not very good for eutectic alloys. So it does not form eutectic alloy is very important that when you consider using a temperature type, because at high temperature, eutectic will melt, so the samples will be either deposited onto the holder itself, or even worse, it will be deposited onto the objective lens. And that can cause a very big issues for the next user. So one thing if you're thinking about doing TEM and things like that is know the characteristics of your sample before doing any of this fancy work. Another thing, of course, is the electric field, especially in Taiwan when we are very famous for electronic products. So how are samples would, have a simultaneous bias under electric field, or in a combination with the temperature is also something we come and look at. This is very interesting for those who are in the semiconductor industries or those in general electronic fieldwork. The third one is slightly more unique, is when we are pumping gas and heating through this sample holder itself. So we can see that there is an O-ring on it, so it's a little bit thicker that we can kind of inject gas. This is particularly of interest since nowadays we have been facing the human society challenge of energy crisis, environmental protection. So for things like nanotechnology or nanomembranes, these sort of in situ holders are very useful for us to understand how the gas or the volatiles or the environmental pollutions are reacting with a catalyst. Okay. So the nano world is now kind of a heat to trying to provide a solution to these global challenges. Okay. And then what this is that it enables us to go up to probably 1 bar of pressure inside this TEM, and then trying to see how the catalytic work is happening at microscopic scale. So these are the holders itself. Now we're going to talk about how to put the specimens in the holders. Okay. So there's things that we can't neglect, is that this whole chamber, this whole thing is still under a vacuum status. So the holder itself for the TEM can heavily influence on the resolution and the specimen interactions. So more importantly is, will it break this holder? Nowadays, the vacuum system is probably automatic. You press a button and it does it automatically. You have no control over much things. But your carelessness on how you deal with your sample can heavily degrade the vacuum system itself. This includes touching the rod with your greasy hands. This includes not wearing gloves. Okay? You shouldn't be touching the rod without wearing gloves in the first place. Okay? So how you drop your samples onto the holder itself, that is also very important. So normally we have the grid, which is probably copper or something like that. And it is what we call a mesh. So this is a gold plate, and there is kind of a sticker sort of thing which we put on it. That sticker-like thing is a carbon film. So these carbon films, they comes in two types, which we call it the lacy holder and the holy one. So the lacy carbon support film provides a range of hole size, as we can see. It's not so uniform, but it offers a solution of continuous carbon film that maybe is not desirable, but it is relatively cheaper. Okay. The lacy carbon support films are much more robust also than the holy carbon support films, and is very good if you require a rigorous pre-treatment of your samples. And also, the lacy carbon support film offers a much more open areas than holy carbon films, which resembles a random mesh, as we can see here, which is also ideal for using like graphene and oxide type. The second one is the holy one, which, as you can see in the cross section, that the holes are much more evenly distributed on the carbon. Okay, so this is how we drip our specimen, and now is how we put it into the specimen stage. So as you can see at the bottom, that there are very many different types of specimen stage nowadays. Okay, so we have the vacuum ring, so like an O-ring to ensure the vacuum doesn't leak. We have an orientation switching pin, so it's kind of a dummy-proof device. And then we will put the samples in the little hole at the top, as you can see at the bottom. So there is something called a single tilting, double tilting, multi-loading. I'm sure there's much more too. So what it is you can load 1 or 2 samples onto that. But the most important thing is that you lock it in properly. So there's a screw-in locking ring. Please put that in properly. Otherwise, as you're tilting your sample, it is very likely that your sample will just fall off into the system. That means we will be having to shut down the whole TEM machine and get your specimen out. Okay, that is not desirable for you or for your supervisor. Okay, so one thing to be careful. And remember, please do not touch the rod itself, okay, because that will compromise the vacuum system. That's one thing to be careful of. Okay, so we talked about how to put the specimen in and how to drip it on and how to choose the carbon lasers. Now let's focus back onto the TEM machines. Okay. So there are 2 modes of the TEM machines, the image mode and the diffraction pattern mode. Compared to SEM, the TEM machines, we care much more about the optical alignment. So as you can see here, we don't move anything in that. We have it aligned from the manufacturer. We have it aligned by whoever is dealing with the management, and we don't touch anything else. The only thing that we play with is the magnet strength, so the lens. Okay, so we have the lenses, the strength of the lens. We'll play with how the beams are being diffracted, being distributed, and from that we can see either diffraction pattern, which we can see on the right, which gives us the crystallographic information of your material, or on the left you can see that we can give us the image of your materials. This is particularly important if you're dealing with the nanoscale specimen. Right, so let's talk about how we get the diffraction pattern. So those dots. On the left, you can see that this is the basic outline of what TEM column looks like. So from the outside, you can just see, a long straight column, but inside it is very busy. There is the electron gun with the accelerator at the top, as we have mentioned also in SEM. And we have then the condenser lenses all the way through, and then the objective lenses at the bottom. So here we're dealing with the diffraction mode, which means that the electrons are emerges from the exit surface of the specimen and disperses down to form a diffraction pattern back in the focal plane. Okay, so it goes back in the back focal plane here. We can adjust the image lens, so the BEF of the objective lens also acts as the objective plane for the intermediate lens. So we're playing around here with how the alignment of the optical rays are going to see how it goes up or down or fat or thin. Okay. So the diffraction pattern is then projected onto the CCD or the viewing screen at the end. Okay, so this is where we get the dotted patterns where we can calculate what phase we're doing here. Just to note that what we can show here is a very, very simple version. Nowadays, there's going to be much more lenses. There's really rarely just have 1 or 2 lenses in the column. Okay, at least 3. Okay. So apart from the diffraction pattern mode, of course, as we mentioned, there is the image mode. So this is the recombination of all the things that I said in the diffraction pattern mode and what we have of the above in the image plane. So we're just changing what the plate is. So we readjust the intermediate plane. So the objective plane is now the image plane of the objective lens. This is a really big mouthful, I understand. So probably you guys need to go back to learn about how the general physics of how lenses work before your head explodes trying to understand how this works. So what we have, again, the image will be projected onto the viewing screen or the CCD. Nowadays, the viewing screen and the CCD are probably a monitor. Back in the old days when I was doing it, it is a fluorescence screen, so you look like Halloween all over again. But you guys are lucky now. It's just a monitor nowadays. And we can see that at the bottom of it, there is the electron energy loss spectrometer attached to the end as well, which is something that we will be discussing about. And then there's also in the middle is the SAD aperture, the selected area diffraction aperture here, and the X-ray detector, which is sited in the middle, which we will talk about next. Okay, so the selected area of electron diffraction, which we just call it a SAED, what we do is to look at the specific area that contribute to the diffraction pattern and reduces the intensity of the beam. So as you can imagine, it's a selected area, so we look at a selected area, a specific area. So SAED is the standard approach if you want diffraction pattern with a parallel beam of the electrons. We'll talk about parallel beams later on, so don't worry just now. Okay, so how do we reduce the illuminated area of the specimen that contributes to the diffraction pattern? So of course, we make the beam smaller, more specific, okay, hence the name selected area. And what we do is to insert an aperture above the specimen. The aperture, you can kind of think about it like a pinhole. Okay, so we have a pinhole above the specimen. So only those that we want, the signals that we want, will come down to the specimen and we get this selected area. Okay, so this is how the selected area part will work. Okay, so we mentioned about the parallel beam. So let's talk about how we get this parallel beam. Just a note that the parallel beam method is the most common type, but in schematic, we draw it as parallel, but in reality, it's never truly parallel. Okay. As I mentioned earlier, TEM nowadays, it will never just have two condenser lenses. Okay, we made it kind of simplified to have two condenser lenses, but it must have more than two to make it to kind of the standard we want nowadays. So what we do is the focus beam and the probe will enter the specimen, and we can see there is a C1 and C2, which will be adjusted to allow a parallel beam down the column, and then now magnifications up to 100,000. Of course, because we are now in such high resolution, we're now in such high vacuum state, we normally use the FEG gun source, so the one without heat. Okay, so the illuminations have to be much smaller, and we need to magnify the crossovers. The crossovers is when the beam crossing over. Okay, quite self-explanatory here. But that is very important when we're dealing with optics. Okay. So let's look at the first one first. Okay, the A, so the one in the black squared. So what we're here using is that the C1 and C2 is under focus, which means the lens is being weakened. So here, what we produce is the under focus beam type at the bottom, which gives a much more parallel beam at the specimen than what we call over focus. These terminologies are ridiculously confusing, but please, in your own time, work out which one, what is what, and remember what is what. So what we call the lens is weak when the crossover occurs after the plane image. Okay, so if it's strong, it is before the plane image. If it's weak, the crossover is after the plane image. And regardless, we will have an alpha, which is an angle at 10 to the minus 4 radians, which is what we call effectively parallel. Okay. In TEM and SEM, most things will work in radians rather than degrees. In your own time, please try to work out the interchangeability between radians and degrees. Okay. So this is type 1. And type 2, or type B in this type, we use it mainly for STEM or AEM. Slightly more practical situation here. So what we do now here is, to confuse everyone, we have a non-existing but existing C3 lens. What we do is to let the upper pole piece act as a C3 lens there. How to do that is that we have the C2 lens is being focused to produce an image of the crossover at the front of the focal plane of the upper projective pole piece, and then we get a parallel beam of electron being formed off the lens. So what we call here is the denser objective lens system. So this whole system is called a denser objective lens system. So we can see here, regardless of which way you're playing with, we are only playing with the strength of the lenses rather than changing the XY state of anything. Okay, so the lens positions are fixed. The only thing we're playing around with is the strength of the magnets, so we can change how the electrons inside this whole column are being put together. Right, so how to form diffraction patterns? Well, okay, so at the bottom we have the magnetic field and we have the spectrometers. Okay, so there are a couple of types of spectrometers. We're just going to be talking about the serial spectrometer now, which is a single detector that is available. So the spectrum is scanned across a slit by varying strength of the magnetic field, and each energy is detected in turn. So remember, what we're dealing here is how the energy difference correlating to whatever elements we're dealing with. This setup is normally used for early spectrometers. Nowadays, we have multiple types, which we're not going to focus on today. Okay. But of course, the downfall is that this type is much more time consuming because it needs times to go through the different elements or the various wavelength that is coming out. And also, it basically tapes with one energy and then another. That's why it is so time consuming. This one is mainly focused on the magnetic decorations at the bottom. So this part is at the bottom of the prism. Okay, so what we just mentioned in the previous slide there is kind of a basic principle of ILS. So that's giving us information of how each type can be different and how we can scan the elements. So the difference between ILS and EDS, which we have learned from doing with SEM, is that ILS also includes chemical and compositional data available at atomic level, and it's also highly localized. While EDS is unlimited on the thickness because we're dealing with the surface and a high signal to background ratio. The limitation of ILS is the requirement of thin samples, obviously, as we're now dealing in TEMs, which may be difficult in many fields if you're doing with non-nano range or non-thin film applications, and some elements may also overlap. The disadvantage of EDS is that it can cause a non-local fluorescence, which was something we'll talk about later, and low Z limits are limited to a thin film signal-to-noise ratio. But of course, one thing just never forget is this main disadvantage or the main problem with EOS, if you're trying to use it, is that it has to be really, really thin. Because as the sample thickness increases, there is a strong interactions of the primary electrons within the sample results in the electron undergoing many energy loss event. And this trend will reduce the signal to background ratio of the EOS edges. That means we'll reduce the visibility of the edges and reduce in the resolution of what we get. However, of course, the spatial resolution of TEM technique will also be reduced as the thickness increases, losing the quality on the impediment of the overall thing. So we've been talking about a lot of TEMs, the structure, and also the EOS, which is kind of the add-on structures of TEM. Let's talk about the general limitations of TEM. Okay. The general limitations of TEM is we are dealing with a 3D specimen with a 2D image. So as you can see with Mario, if you guys have ever old enough like I am to see the old style Mario, which is a 2D slant. So we are trying to kind of manipulate this 2D image into what we are actually dealing with, which is a 3D specimen. So interpretation of TEM images is of high importance. The next part is the electron beam damage and the safety. The electrons are now at a very high energy level, so it can easily damage your sample. So TEM and SEM are actually both destructive analysis approach. For inorganic method is slightly better because the charge can dispose easily, but for organic and polymer specimens, it can easily cause beam damage. So this is something to keep in mind if you're dealing with organic polymers. Okay, so in a quick summary of TEM setting and its instrument is that, to be honest, the manufacturer has set up a lot for you. So there's not much you can play around with, as we have mentioned multiple times. As long as you don't touch the rod, mess up with the vacuum system, you should be pretty safe. The things you should understand is that the alignment of the illumination system, so the beam is on the axis and can achieve different information. So how the strength of the magnets can change how the alignments of the illumination system, as we have mentioned, and we can achieve different information from that, either a diffraction pattern or an image. The C2 temperature is the critical part of the whole illumination system, and probably most easily to be misaligned. So if you have a bit hazy information, please contact the manufacturer. Do not try to do anything yourself. And if you need to do a diffraction pattern, please remember to always calibrate. If you don't calibrate, your data is mostly useless, and you have to redo them all again. It costs money and time. Okay. Now, astigmatism in TEM compared to SEM is not a big thing here unless you manage to misalign the whole objective. So unless you have really messed it all up, it shouldn't be too much of an issue here in comparison to SEM. Okay, so we have quickly discussed the two parts, the SEM structure, the instrument of how each things are placed, and we've briefly talked about how the TEM been placed, how everything are set up in the column, what not to do, which is to kind of mess up the alignment, and how to deal with the specimen quickly and how to put the specimen in and how to choose it quickly. Okay, that's it for this part.